The end of humanity may seem like a distant theme, but there is an inevitable mechanism already underway. The sun is getting brighter. It is not a sudden disaster. It is a slow but certain transformation. And when the solar brightness increases enough, water will evaporate, climate cycles will collapse, and the Earth will cease to be a habitable planet long before the sun's final death. The sun functions like a nuclear fusion reactor. In the core, hydrogen is transformed into helium, releasing energy. As hydrogen decreases, the core slightly contracts and heats up, accelerating fusion. The result is straightforward. Over time, the sun's brightness increases. This change is small over millennia, but enormous over hundreds of millions of years. Today, the sun is about 4.5 billion years old. It is still in the stable phase of the main sequence. However, in about 1 billion years, the energy received by the Earth will be significantly greater. It seems like a detail, but the planet's climate depends on a delicate balance. Small variations in energy accumulated over millions of years push the system to points of no return. But solar energy means more ocean evaporation. Water vapor, besides being water, is a very efficient greenhouse gas. Thus, a dangerous cycle emerges. More heat generates more vapor retains more heat, and this further raises the temperature. This type of feedback can turn a blue planet into a suffocating world, with a dense and unstable atmosphere. Before any ocean completely disappears, complex life begins to fail. Plants suffer from heat and irregular rainfall. Ecosystems enter permanent stress. Species depend on relatively stable temperature and humidity for reproduction and food. When the plant base collapses, animals cascade into collapse. Extinction would not be a single event, but a long sequence of irreversible losses. Freshwater is the first system to visibly collapse. Rivers cease to flow continuously. Lakes shrink year after year. Food production becomes highly unstable and localized. Even with technology, maintaining agriculture and livestock on the surface would require enormous energy for irrigation, cooling, and protection against increasingly frequent and prolonged heat waves. With more vapor in the air, the atmosphere changes behavior. Storms can become more violent at certain phases, but the overall pattern becomes disorganized. The planet loses climate predictability. And most critically, ultraviolet radiation begins to break down water molecules in the upper layers. This paves the way for the slow loss of hydrogen to space, draining the planet's water over time. When water is dissociated in the upper atmosphere, hydrogen escapes relatively easily due to being extremely light. Oxygen can react with rocks, alter atmospheric chemistry, and over time, reduce the planet's ability to maintain breathable conditions like those of today. This is not a scenario of months. It is a process of millions of years, but it becomes irreversible once certain thresholds are surpassed. Venus is a real reminder of what extreme greenhouse effects can do. There, the atmosphere is dense and hot, and the surface is inhospitable. Earth will not become a perfect copy, but it may follow a similar path. Rising temperatures, loss of liquid water, atmospheric instability, and ecological collapse. The planet does not explode. It simply ceases to support complex life. The last forms of life on the surface would not be large animals. They would be heat-resistant microorganisms living in underground refuges, rock fissures, or geothermal environments. Even so, the survival window for these extremophiles depends on the existence of water and thermal gradients. When water becomes scarce and the planet heats up too much, even these niches will shrink drastically. If humanity still exists when the surface becomes hostile, survival will require extreme engineering. Underground habitats and closed systems would need to recycle water, air, and nutrients with very high efficiency. Outdoor life would become an impossible luxury. Society would become dependent on constant and reliable energy for climate control, atmospheric filtration, and food production in a controlled environment. A more plausible alternative for an advanced civilization would be to live off the surface, in stations, orbital habitats or colonies on other bodies in the solar system. This would not be escape, it would be adaptation. When a planet loses climatic stability, the species that wants to survive needs to change its environment. However, this transition would have to happen long before total collapse, while Earth still provides resources and infrastructure. Mars and some icy moons appear as natural candidates for refuges, each with its challenges. Mars has a thin atmosphere and intense cold, requiring pressurization and protection against radiation. Moons like Europa or Enceladus may have water beneath ice, but they would be complex underground environments. The message is simple. Surviving outside of Earth is only possible with mature technology, abundant energy, and long-term planning. The central point is that none of this prevents the Sun from evolving. The brightness slowly increases due to inevitable internal processes. There is no simple break for this. Even if humanity artificially controlled emissions and climate for a period, the solar increase would ultimately prevail. The planet receives more energy than it can radiate back into space. And when this balance turns positive for long enough, there is only one direction. In advanced stages, liquid water on the surface would become rare and unstable. The water cycle would fail as a thermal regulator. Erosion would decrease, rivers would cease to exist as we know them, and the planet would become dominated by arid environments. Any attempt to maintain biological human life on the surface would depend on total protection, as if the Earth had turned into a hostile alien world. Closed biosphere systems, such as pressurized greenhouses and vertical farms, would become essential. And for this to work for centuries or millennia, an entire economy based on maintenance would be necessary. It wouldn't just be about surviving the heat. It would be about living on a planet that has ceased to naturally provide the basic services that today seem free: breathable air, accessible water, and moderate temperature. With photosynthesis in decline, atmospheric oxygen would decrease over time. This alters respiration, combustion, and the entire chemistry of the planet. It's not a secondary detail. For humans, oxygen is biological infrastructure. The loss of atmospheric stability adds yet another gigantic barrier to survival. And when multiple barriers accumulate, heat, water, air, the entire system converges towards unviability. It is important to understand scale. The deadline is not tomorrow, but it is also not infinite. The limit of habitability for complex life on Earth is estimated to be around 1 billion years, depending on the climate and geological model. Uncertainty does not change the outcome, it only adjusts the date. The general path is inevitable. More solar brightness, more warming, less stable water, less complex life. This story doesn't have to be just a sentence. It can be a philosophical and technological push. If humanity wants to last, it needs to learn to live in more than one world. The concept of a multiplanetary species is not just ambition, it's a survival strategy on a cosmic scale. Earth is an extraordinary cradle, but no cradle is an eternal home. The universe does not provide permanent guarantees. Real spatial migration requires energy, materials, knowledge, and, above all, time. Building infrastructure off Earth depends on what Earth can still provide. Therefore, civilizations that expect the collapse to come first may find out too late that there is no longer a foundation to escape. The critical point is not when the planet becomes impossible. It is when it becomes too difficult to sustain large-scale exit. So far, we have discussed the unfeasibility due to heating and water loss. But the evolution of the Sun goes beyond that. In the long term, the Sun will change phases, alter its size and its behavior. And even if humanity becomes multiplanetary, the entire solar system will change. Understanding the future of the Sun is understanding the future of our civilization, because civilizations also depend on energy, stability, and predictability to exist. As the Sun ages, it approaches changes greater than the slow increase in brightness. It will begin to expand toward the red giant phase. This happens in billions of years, but preparing to survive a transforming stellar system would require an extremely advanced civilization, capable of changing orbits, transferring populations, and creating habitats independent of a single planet. The inner orbits can change over time due to gravitational effects and mass loss from the Sun in later phases. This can push the Earth away, but it does not save habitability, because climatic unviability occurs much earlier. That is why the two times are different. First comes the biological end on the surface, caused by warming and water loss. Then, much later, comes the physical fate of the planet in front of an expanded star. If you could visit the Earth in that distant future, you would see no oceans, no forests, nor signs of civilization on the surface. You would see a dry, hot, and silent world. And the strangest feeling would be realizing that nothing attacked the planet. There was no external villain. There was only physics. The same physics that allows our existence today is the physics that defines the deadline for habitability. This puts the present in perspective. The planet is still extraordinarily hospitable. We still have water, air, and a climate compatible with complex life. But this period is not eternal. Understanding the extreme future of Earth is not just curiosity. It is a reminder of how rare, fragile, and precious life is in a vast universe. If we want to last, we need to think as a civilization, not just as a generation. In the next part, we will move on to the final scenario: the complete degradation of the oceans, the decline of oxygen, the definitive collapse of the biosphere, and the red giant phase. We will also answer the most uncomfortable question of all. When Earth ceases to be a home and becomes just a hot rock in space, what would remain of humanity? And where would it need to go to continue existing? Stay with us. When evaporation dominates, the land enters a climatic state where water ceases to be a regulator and becomes fuel for heating. The atmosphere becomes laden with vapor, retaining heat day and night. Even without reaching the immediate extreme, this process drastically reduces the habitable zone. The surface becomes a place where each additional degree pushes ecosystems toward collapse, and the recovery time disappears. On a planet warming due to the sun, there is no comfortable, new climate equilibrium. There is instability. Some regions may experience violent rains, but that does not mean abundance. It means excessive energy in the system. And then, longer droughts. For humans, the difficulty is not just heat. It is predictability. Without predictability, infrastructure fails, agriculture fails, and urban life becomes a permanent exercise in crisis management. The most dangerous step is invisible: the gradual loss of water to space. When water reaches the upper atmosphere, ultraviolet radiation breaks it down. Hydrogen escapes. The planet loses a resource that took billions of years to accumulate. Every million years, more water disappears. And what this means is brutal. Even if the planet cools for some local reason, the water does not return. The cosmic tap closes. With less water, the land loses an essential mechanism for energy distribution. Oceans and ocean currents transport heat around the planet. Without them, the temperature difference between regions becomes extreme. This alters winds, pressures, and the entire climate pattern. Some areas may become permanent furnaces, while others may experience violent fluctuations. For a species like ours, dependent on stability, this is the beginning of a biologically incompatible planet. As plants cease to thrive, the decline of oxygen becomes inevitable. It is not an instantaneous collapse, but rather a decline. Without robust photosynthesis, oxygen is not replenished at the same scale, and without oxygen, complex animal life disappears. Humans, even in shelters, rely on artificial oxygen production, which further increases dependence on energy and technology on a planet that no longer cooperates. From a certain point on, living on Earth would be similar to living in a submarine or in a space station, only on a continental scale. The external environment ceases to be a place to exist and becomes a constant threat. This transforms society. Each person comes to depend on networks of energy, maintenance, and materials. Any systemic failure, whether due to scarce resources or technical collapse, stops being an inconvenience and becomes a matter of immediate survival. When the surface becomes uninhabitable, life retreats downward. Caves, remaining aquifers, deep fissures. But these refuges depend on water and stable chemistry. With the planet becoming increasingly dry, even the refuges turn into isolated islands. Therefore, even extremophile microorganisms would not have infinite time. The Earth would not only change in type, it would continue marching toward an increasingly sterile state. Many people imagine that the Earth's hot future would be like an eternal summer. In fact, it is something much worse. A system locked in heat and pressure, with an atmosphere dominated by gases that trap energy and prevent effective cooling. Venus shows that a planet can be stuck in this state for geological time. The difference is that, in the case of Earth, the main trigger is the evolution of the Sun, which continues to push the system in the same direction. When the oceans shrink, the planet loses the visual signature that makes it alive. Fewer clouds, less blue, less contrast. But the real change is functional. Without water, the chemical cycles break down. Nutrients stop circulating. Soil ceases to be fertile. Complex life becomes the exception and then disappears. The Earth still exists as a rocky body, but the idea of a habitable world ceases to make sense. That is when humanity should have already left. The most realistic exit for an advanced civilization may not be a new planet, but built habitats. Space cylinders, giant stations, orbital cities with artificial gravity. Instead of looking for another Earth, humanity would create controlled environments, independent of Earth's climatic collapse. This would require colossal engineering, but it has one advantage. It does not depend on the geology and climate of a planet. It relies on energy, materials, and technological continuity. To sustain habitats outside of Earth, resources would also need to come from outside. Asteroid mining and processing materials in space would reduce the need to extract everything from the home planet. This is the kind of transition that separates a planetary civilization from a spacefaring civilization. And here comes a crucial detail. The window of opportunity exists while Earth is still functional. When the planet is already too degraded, making this transition becomes more difficult. The increasing brightness of the sun is a slow process, but irreversible. So the problem is not if the planet will become uninhabitable, it's when and how soon for complex life. The scary part is that uninhabitability arrives before the physical end of the planet. Earth may continue to orbit for billions of years and still have lost water, oxygen, and any complex ecosystem long before. Around 5 billion years in the future, the sun enters the red giant phase. It expands enormously, completely changing the inner solar system. But note, humanity cannot wait for this event to act, because habitability will have already ended long before. The red giant phase is the final signature, the last chapter. The chapter in which human life leaves Earth happens much earlier, due to heat and the gradual loss of the oceans. There is debate about whether the Earth will be swallowed by the expanding sun, as tidal effects and stellar mass loss alter orbits. But this is almost irrelevant for life. A planet can survive physically and still be biologically dead. If the Earth escapes being swallowed, it will still face extreme temperatures, possible surface melting, and total sterilization. In any scenario, the planet will not be a home. In the final stage, the crust can heat up to levels capable of altering minerals and releasing gases. The atmosphere, if it exists, will be the result of reactions with rocks and remnants of volatiles. Liquid water is no longer part of the system, and without water, the chemistry of life has no space to operate as we know it. This means that the planet, even though it continues to spin, becomes a hot and silent rock, without oceans and without a biosphere. When we imagine extinction, we think of a dramatic moment. Here, extinction is a trend. The environment becomes less compatible, step by step, until human life becomes mathematically unviable outside of artificial systems. And even within these systems, sustainability depends on industrial and energy chains. Without maintenance, everything falls apart. Therefore, human survival is not just biological, it is logistical. It is civilizational continuity. Energy is the axis of everything. To withstand external heat, produce water, generate oxygen, and grow food in a controlled environment, a civilization needs stable energy sources for enormous periods. This can include solar energy, but also fusion, advanced fission, or future technologies. The paradox is that increased solar brightness brings more available energy, but it also brings more thermal danger. It's like gaining fuel while the engine starts to melt. The most robust strategy is not a single colony. It is a network. Multiple habitats, various orbits, different resource sources, multiple supply routes. When you have redundancy, a failure does not wipe out the species. That is what life does on Earth. It spreads, diversifies, and creates natural backups. Humanity that wants to last needs to replicate this logic, but on a spatial scale. Relying on a single world is accepting a single point of failure. In the end, the story of the sun teaches us something uncomfortable. There is no eternal planet. Every stellar system evolves. Every stability has a deadline. So what defines the duration of an intelligent species is not just how comfortable its home planet is, but how quickly it learns to move, adapt, and create new homes. Human extinction on Earth may be inevitable. Human extinction in the universe does not have to be. Looking at that distant future also changes the value of the present. The Earth has oceans, a moderate climate, and a rich biosphere, rare things in the universe. This balance is not guaranteed forever. It is an interval, and intervals can end. Understanding the timeline of habitability is not meant to instill fear, but to provide perspective. If one day we are great enough to leave here, it will be because we learn to respect what we have now. Estimates of when the Earth becomes uninhabitable vary according to models, because climate, geology, and atmosphere interact. But the direction of the process is robust. More brightness, more warming, more evaporation, more water loss, less ecological stability. The details change, the fate does not. And this distinction is important. We are not talking about guessing. We are talking about physical trends sustained by stellar evolution and atmospheric chemistry. The most common myth is to imagine that the planet always finds a way. But systems have limits. When liquid water ceases to exist on a global scale, the planet loses one of the pillars of habitability. And when hydrogen escapes, you don't easily recover oceans because the raw material is gone. This defines a point of irreversibility. That's why the time window is so relevant. It's not just about heat, it's about losing the most fundamental resource. If humanity wants to survive beyond Earth, it needs to start early, not late. Building space infrastructure is a civilization project, not a generational one. It involves education, energy, industry, and social stability. It also involves vision, accepting that the home planet has an expiration date, even if that date is much longer than a human life. Intelligent species are rare, and perhaps intelligence exists precisely to perceive the future and act before the future becomes an emergency. One day, the Earth will be just a dot among billions, a world that was once home to oceans, forests, and cities. The deeper question is, will this be the end of our story, or just the first chapter? Because extinction on Earth does not have to mean the extinction of humanity. It could be the definitive transition to a species that does not depend on a single planet. And it is this difference that separates destiny from choice. When you understand the scale of solar time, you realize that humanity has two ways to disappear: through the inability to leave the planet, or by making poor choices long before the inevitable warming arrives. The threat from the sun is distant, but it demonstrates a principle. Civilizations that endure need to plan for the impossible. They need to build the capacity for survival outside the place where they were born. Because the universe is not stable, and stability has never been a promise. The sun will make the earth uninhabitable. That's physics. But what happens to humanity until then is history. If you want more videos that explore the extreme future of the universe, the fate of the earth, and the limits of life, follow us.